we're going to discuss converter circuits. First, we're going to discuss where these converters come from and what are the relationships between them. So we have already introduced some different converters, such as the boost or the buck boost, or some others that we have done in a few problems. So let's just talk a little bit about what the relationships are between these and how you can derive one from the other. Then second, we're going to discuss transformer isolated converters, which so far in this course have not been covered yet. So we will talk about the important topics of how we can introduce a physical magnetic isolation transformer into a power converter, and discuss some of the well-known and widely used isolated converter circuits. So we'll begin this discussion, circuit manipulations, and what we're going to discuss here is how to take a converter we already know and manipulate it to generate a new one, and to perform some new function that we want. So what we're going to do is start with the buck converter as the original rudimentary converter, and at the beginning of this course we've already taken a basic idea about this converter, that we have a switch network that changes the DC component of the voltage, and then this is followed by a filter that removes the switching harmonics and passes this changed DC component to the load. And we know now from all of the analysis and basic arguments that the conversion ratio of the buck converter is M equal to the duty cycle, where this conversion ratio is the ratio of the output to the input voltage. Okay, now something that we can do to a converter is, first, we can consider changing the positions of the power source and the load. So here we've drawn kind of a box around the buck converter where we have input terminals labeled V1, where there is a source of power connected, and we have the output terminal that's labeled V2 here, where we've connected a load with a filter capacitor. So power flows from the source to the load, and we know, since this is a buck converter, that V2 is equal to the duty cycle times V1. Now one thing that we can do is connect our power source to port 2 and our load to port 1. And here's an example of that. So here we've connected the power source to V2 and the load is in V1, but the relationship between V1 and V2 is the same. In fact, if you apply volt-second balance to this inductor, you'll find exactly the same relationship, that V2 is still dV1, but now V2 is the power source and V1 is the load. So if we solve for V1, we find that V1 is equal to V2 divided by D, the duty cycle. And since the duty cycle is less than 1, the load voltage V1 is greater than the source voltage V2. So this performs the function actually of boosting the voltage. And in fact, if you look at this carefully, you might recognize that this looks like a boost converter, just drawn from right to left instead of from left to right. By interchanging the source and the load, what we've done is reverse the direction of current flow. So this actually makes current flow the other direction through the inductor. And as a result, we have to look at carefully at how we realize the switches. So back in the previous chapter, we introduced a formal way to realize the switches, and if we apply that process here, what we find is that we have to put a transistor from the switching node to ground, and we have to put a diode from the switching node to port 1, which is quite different than what we had to do in the buck converter when the current flowed the other direction. And something that this does is that it actually changes the definition of the duty cycle. We can define the duty cycle as being the fraction of time the switch is in position 1, or we could define it as the fraction of time the switch is in position 2. It's really just semantics. We typically define the duty cycle according to the transistor duty cycle, and here when this transistor is on, the switch now is in position 2, not 1. In fact, we can just define switch position 1 as when the transistor is on, and if we do that, we have to interchange D and D prime. So V1 we then write as 1 over D prime times V2 instead of 1 over D, and this then is in fact the traditional equation for the boost converter. The output voltage, which is now V1, is 1 over D prime times the input voltage V2. So the D prime comes simply because power is flowing in the opposite direction and we have to realize the switches in a different way. So the boost literally is simply a buck converter connected backwards. Okay, a second thing we can do is we can connect converters and cascade. So take your favorite converter and make, let's call it converter number 1, and if we know its conversion ratio, so the output voltage of converter 1, V1, is equal to this conversion ratio M1 of D times the input voltage VG, and we can take that voltage V1 and use it as the input of a second converter. So take your second most favorite converter and put it there as converter number 2, and its output voltage that here we will apply to the load is the conversion ratio in 2 for the second converter times V1. Okay, so the overall conversion ratio of this cascade then is V is equal to M1 times M2 times VG, so we get the conversion ratio of M1 times M2. Okay, well that's fine, but let's try it. So I think a straightforward thing to do might be to take a buck converter and put it as converter 1 and a boost converter as converter 2. So this combination is capable of making an output voltage that is either less than or greater than VG, depending on the duty cycles of the individual buck and boost converters. Okay, and so in fact, if we drive the switches of the two converters with the same duty cycle, then what we get for the cascade connection is D over 1 minus D, which sounds like a buck boost type conversion ratio. And here literally is the circuit then. Here's our buck converter, the switch, and the LC filter. The output of the buck becomes the input to the boost converter. It has its switch and its LC driving the load. Okay, well that's all fine. However, there are some things that we can do to simplify this circuit. And for one thing, if you look at this inner part of the circuit, we have a 3-pole low-pass filter. So there's an inductor, then a capacitor, and then another inductor that are filtering the ripple. Now you can do this if you want, but we don't really have to. We can reduce the order of this low-pass filter, and the basic DC waveforms will be unchanged. Changing the order of the filter merely changes how it filters the ripple. So for example, we could remove C1 if we like, and once we've done that, we have two inductors in series, and we can combine the series connection of the inductors into one inductor. So here's that. We have the two inductors in series, we combine them into a single effective inductor that's a sum of two inductances, and we get this circuit. Okay, this is called the non-inverting buck boost converter, and it's actually a popular converter. It's widely used in applications such as mobile computing and cell phones, where we need an output voltage that is either greater than or less than the input voltage. And we actually don't have to control the two switches networks with the same duty cycle. You can switch, for example, just one and not the other if you want, and that turns out to be a good way to control them. So if you want to boost, we make the buck switches just always connected in position 1. and we operate the boost switches with some duty cycle to control the boost ratio. And conversely, if we want to buck, we just leave the boost switch in position 2 and we control the buck switches with some duty cycle to control the buck ratio of the converter. This is a very efficient converter, and especially if the output voltage is near the input voltage, we have a low switching loss and low conduction loss in this converter, and it can operate with very high efficiency. So there's something else we can do to this non-inverting converter. If we look at what this circuit is with a switch in the two different positions, and let's assume now that we operate both switch networks with the same duty cycle, then with the switches in position 1 and inductors connected to VG, and we put a dot here to just follow the polarity in which the inductor is connected. So the dot is connected to VG and the non-dot side of the inductor is connected to ground. So we have this circuit for subinterval 1. In subinterval 2, we have the dot side of the inductor connected to the ground and the non-dot side connected to the output like this. Okay, so this is what we just described, and this is the non-inverting buck-boost converter. Now, one simple thing that we can do is change the polarity of the inductor during one of the intervals. So for example, during subinterval 2, if we just reverse the direction of the inductor and connect the dot side to the output and voltage instead to the ground, like this, then that would change the polarity of the output voltage. Our inductor current, instead of flowing in this way to the output, will flow the other direction and cause a negative output voltage. Otherwise, this is the same circuit as before. So this is called the inverting buck-boost converter, and it turns out to reduce the number of switches necessary. Because if you look at this, the non-dot side of the inductor is always connected to ground. And all you have to do is connect the dot side either to VG in position 1 or to the output voltage in position 2. Okay, so here are the two subintervals, and we connect a switch like this, as we've mentioned, and what we get then is the inverting buck-boost converter, which is what we have talked about previously in this course. So the inverting buck-boost converter can be derived from the cascade connection of a buck converter and the boost converter. And then by reversing the polarity of the inductor during one of the intervals, we simplify the number of switches needed, and we get a minus sign, so it's an inverting converter. Okay, so cascade connections of converters then can actually lead to new converters as well. We cascade two converters and then simplify the result, and we can generate a new converter with properties that combine the properties of the two individual original converters. If you construct the equivalent circuit model of the buck-boost converter, what you find is that you actually get two DC transformer models in it. There's a buck transformer, and later there's a boost transformer in the equivalent circuit model. And this actually reflects it, the origin of the buck-boost converter. It is in fact a cascade of a buck followed by a boost. There's other cascade connections possible. We just took one, arbitrary one. Another well-known cascade connection starts with a boost and followed by a buck. So we have boost first and buck instead of buck followed by boost. And if we do that and follow the same arguments that we have applied to the buck-boost converter, what we get in this case is a Chook converter, which is named after its inventor. And he actually derived this converter best by cascading a boost followed by a buck. Now you can plug other converters in and follow them. We're not going to do that, but as an exercise, it might be an interesting thing to try to do and see what other kinds of converters you can generate.